the periodic table. Now there are a bunch of elements in the world where different substances. There's gold, there's silver, and also bronze, which would be when copper and tin together, that is bronze. So a bunch of substances. Some can be put together like copper and tin, that becomes then bronze. Or just gold or silver or platinum or something else. All these elements, they have to be sorted, and 109 are known in this book when this book was written. A few found since then. A few were found since then. Now, these 109 elements, they have to be sorted. They have to be sorted in some way. And the periodic table is the way to do it, which is a way which is often used to do it. And there was Dmitri Mendeleev, and in 1896 he published his idea how to sort them. He took every element which he knew about, without all the information down on the card, sorted them and published it then, and that was his result. So all the elements down, 1, 2, 3, 4, 5, 6, and so on, all the elements, 109 down in these lists. These lists are the periods, and that are the groups. It's like that. And they all have similarities, and someone who understands, is like that written in the book, how they are sorted there, can, by just looking at where they are written, know something about how this element will behave alone or with another one together. And now it is like that. There are different groups. There are the alkali metals, and then the alkaline earth metals, the transition metals, the lanthanides and austenites, and then the poor metals, the semi-metals, and the non-metals, and the noble gases. So all these groups. And they behave almost all similar if they're in such a group. So if someone understands it, they know it is written in the first group or the second group, that element will behave like that. It will burn at that degree, it will make then fire, it will react with other thing strongly, it will make something, it will shatter, it will make it going away, so it will make a solution out of it. How it will behave, basically. What will it do with another stuff? Will it be just peaceful there, or will it react? And for example, all these metals together, they have something similar things. Metals, they are solid at room temperature, a part of mercury for some reason. So solid, they conduct heat good. That is why if someone touches a metallic thing, it feels cold because warmth is going fast away. And other things, they are not like that. It goes not so fast away. Air, for example, is gas. And gas is not transporting the heat so fast, and also does not conduct the electricity so good. But metal does, and that is why cables are out of metal and stuff like that. So someone who understands it knows metal stands there and there and there, and they know out of that could be done a cable, or that stuff will react together with that, and so on. So something's there. How they are written there? Where is then written for carbon, for example, is 6 at the top, and then the C, then carbon, and then 12. The 6 means it has the atomic number 6. So someone could say atomic number 6 is carbon, or carbon has the atomic number 6. And that means that carbon is the 6th element in this list. There's 1, 2, 3, 4, 5, 6 somewhere there. And that 6 is the amount of protons in the nucleus. Such an atom has in the center of the nucleus, and then around it, shells, called like that. I don't think they're actually existing, but it's just called like that, shells, and on these shells are the electrons. So such an atom looks like that. In the center there is the nucleus with a proton in it by the atomic number carbon, 6. And then out of them, on these shells, however that now actually looks with these shells, there are now 6 electrons. So the same amount of protons has such an atom as electrons. And atomic number 6 says 6. Gold has whatever, 64, whatever. That means now 64 protons are in there, and the lead has 79 or whatever, and there are now 79 protons in the center and 79 on the outside. And these shells were starting like that. They're first a shell of 2, and then there are 2 electrons are on it. So that is for hydrogen. Hydrogen has the atomic number 1, and then helium number 2. Hydrogen has now 1 proton in the center and 1 electron then on the shell. Helium has now 2 protons in the center and 2 on the shells. And that is why we are so far apart written, because the shell is already full. I think that is the reason. So it doesn't look completely like rows, because these shells are differently. The first shell can only hold 2 electrons, the after ones 8, and probably even more. And so they're not written like 1, 2, 3, 4, 5, 6, 7, 8, or 10, so 1, 2, then 3, 4, 5, 6, 7, 8 or something like that, and then more or less like rows. And all the one in the first row, they have 1 electron on the outside. And the last row, there they have 8 or full. It wasn't said directly in the book. They are the electrons been full on the shells. Now, and that has a lot to do with how they react. Some electron with one on the outermost shell. If there's 1 electron on the outermost shell, that can easily react with another substance as if there were 2. So it has an influence how many are on the outermost shell, because that electron can be lost or gained. 1 electron can be gained to an atom and lost. So where they are, tells them how they are reacting, because all the one in the first row have one electron on the outside. That one electron, which is there on the outermost shell, so there's the nucleus with all the protons in it and neutrons also, and then all the electrons on the outermost shell, and all elements in the first group have one electron in the outermost shell. And therefore all these atoms in the first rows, these alkaline earths, have a similarity how they will react with other metals because they have one electron there. It's like a puzzle piece. That puzzle piece will fit together with south one who has 4, 3, 5 or 6 electrons in the outermost shell. And we're going always up. Every one further, one group further, or one row further, it's not said so directly here, as in one more. So one electron outermost shell, 2, 3, 4, 5, 6, 7, 8. So that is why there can be something read about how it all works. And maybe some interesting fun fact would be, the more protons are in the center, the more we're pulling in the shells. So actually the amount of atoms increases down the period with 15, 16, 17, 18, 19, 20 and so on, but the atom decreases in size because there are no more protons in the center pulling in the electrons on the outside. As a little fun fact. Now, and that is according to Susan McKeever's Science Encyclopedia book, written on page 32 and 33. Hi, Becca. I'm trying to learn chemistry today, the periodic table, and after we've done that, we're gonna do wrist training. And if you participate in the wrist training, then it's better to honest. The periodic table. This complicated looking table is really a simple list of all the elements. That is a list of all the elements. They are arranged in rows in order of increasing atomic number, or number of protons in the nucleus. So we can count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and so on. And that is the amount of protons in the nucleus. During the 1860s, chemists noticed that certain groups of elements behave in similar ways and tried to set the groups out clearly in a table. In 1869, Dmitry Mendeleev published the best table, which is still used today. A chemist can tell a lot about an element just by looking at its position in the periodic table. So all these, we're going here until 109, I think, elements are here listed, which exist. Maybe there's 110, 11, 12, 14, something, but it's more or less until 109. I think there are a few more, but 109. And these are all the elements out of which all exist. And they are listed in this, and there are a bunch of elements, and the people thought, how can we set them together? And they said, basically, there are some elements with one atom, one proton in the center, and others have 5, one has 5, one has 6, one has 7, one has 8, and so on. And they probably noticed that there is one element which is one proton in the center, another element with 2, another element with 3. And there is no other element which has 4 in the center as that one which it is, and it is beryllium. Now let's take an easier one which is understandable. Silver, 47. So they found an atom, and that, I don't know if they had it that way around, but they found an atom and that had 47 protons in the center, in the nucleus. They found silver, they looked very closely in it, and they found that when we go very closely into that silver, that every single silver, little tiny particle in it, had 47 protons in it. And the other piece of silver as well, and as well. And they couldn't find another stuff with 47 in it. Then we took maybe, they did not do it, this would be something optional possible. We took then something else, for example here, we took gold, which is somewhere, I think it's 64. You can't find 64. 64 gadolinium. No, that is it not. No, we found them gold sometime, and then we looked in that, and then we counted, and we found 79 protons. And in everything of them, that would be a possible way to do it. We did not do it that way, but that would be a way to do it. That is a way to understand it. And they found on each piece of gold 79 protons in the center. In each silver piece, it was a 47. And they took another gold piece, and it was always 79 protons in the center. And there is no other element as gold with 79 protons in the center. If it has 80 in it, it is mercury, a completely different thing. If it has one less, it is platinum. Platinum is a completely different element than gold. There is no second stuff, material, with 79 protons in the center as gold. And every gold has 79 in the center. And that is why gold has the number 79, because every piece of gold, every little atom inside of gold, has 79 protons in its center. And they took silver, looked in it, but silver has always 47, never 79. And that is silver. Every piece of every atom which has 47 protons in the center is silver. If it has 48, it is cadmium. If it has 46, palladium. And that goes on with all these elements. And these are the ones understandable because they exist like that in the world. So silver or gold or platinum or palladium maybe also, or nickel and copper. Some other ones are a bit more complex. Oxygen, what is it? It's in the air, but what is it now really? Or neon, argon, chlorine, sulfur. They all exist, but they're a bit more complicated. But all these elements are their number and protons in the center. And we found one element which is 1 proton in the center, another one with 2, 3, 4, 5. We found an element with 40, another one with 41, 42. And they tried to find a way to list them all. And maybe we wrote them down in one list. But there's more to it than just the proton number. Atoms have on the outside outside shells, and there are electrons on them. And now the people went there and looking, it is not only able to sort them just by the number of protons in them, 1, 2, 3, 4, 5, 47 silver, 79 gold, but they said there are electrons on the shells. And there's the same amount of electrons outside on the shells as there are protons in the center. And they are not always the same order. Because having them all in the center, in the nucleus, in the center of the nucleus of an atom, these 79 protons of gold, that's easy, they're just in the center. But having those 79 electrons on the outside, on rings outside, so there's the nucleus, and then there's a ring, another ring, another ring, another ring. Having those 79 electrons there, that is way more complicated. They can be everywhere structured, technically. So now it becomes interesting, because now it's looked, how do they fit now together with other ones? Because now it gets more interesting. Why sorting them like that complex? Why not in a list down? Let's read a bit on what we now explain as next. The atomic number is the number of protons in the nucleus. It goes up one by one along each period. So the first number 1 here, that is the number of protons in the nucleus, and that is also the atomic number of it. So your silver, atomic number 47, it has 47 protons in its nucleus. The symbol, now by silver Ag, the symbol is a shorthand way of writing the element used in chemical equations. Sometimes writing the name like molybdenum is just too complex. Molybdenum, and the people just write MO. And that is easier. Some of these names are a bit complex, where they come from, these names. Why? Because just sorting with 1 or 2 letters down can be a bit complex. And that gets a bit complicated, but it's oftentimes zinc is Zn zinc. Some of these things are Latin-based, other things. Gold, for example, they are 79. It has Au, because the Romans called it aurum or something. Written with AU, aurum or something, or whatever. And so there are some named after some complex things, but it's basically just a shortened form of a word. Carbon has just a C. So whenever a chemist writes a C, they mean carbon. And then the 12, the relative atomic mass is the mass of the atom compared with the mass of carbon-12 taken as 12. Now we're coming to the point which I don't really understand. The relative atomic mass is the mass of the atom compared with the mass of carbon-12 taken as 12. That is the mass of the element. That is what we're talking about. That is how heavy that thing is, basically. How much weight it is weighing. And I don't really understand the taking of that, what we're basically saying. Basically, we're saying that is how heavy it is. And it makes sense. If you look at it, we're having here 1 hydrogen, and then here helium. And these are gases. Helium is a gas in air balloons, and hydrogen is in the air. I think, I don't know. Hydrogen is somewhere. These are gases. They are very, very light. They're so light that they're going up. The helium balloon goes up. And when we're getting a bit more heavy, maybe aluminum with 27. And that is a bit more heavy. And when we're going further down, iron has 56. So I don't really know how it's better. One atom of iron weighs 56. I don't know what we're now talking about here. That is how heavy it is. That is basically all the decision here. How it's now calculated, a bit more complex, but it's just how heavy it is. And we're having silver with 109 and gold 197. Gold is pretty heavy, 197. And this is just what is standing there. And now we're having a little key here. Where are the alkali metals? These are them here on the side. Others men. Let's say these are alkali metals. I think that are the part of hydrogen. Now, and the idea behind it is that they are not listed after something, but that it is able to make a sense in it. Not just after the atomic number, 1, 2, 3, 4, 5, 6, 7 down, but there are also some alkalic metals. And the idea is now to write them down in a way that all these alkalis are written down in one line. But this is after the electrons. This is written somewhere here, I think. I saw something just a moment ago. So all these colors also mean things. If something is noble gas, they are here. Helium is a noble gas. Neon, there's some lamps used, or krypton, argon, xenon, and radon. So these colors mean that they are part of these type of stuff. For example, other than metals, or alkali metals, or poor metals. So some things. How does the periodic table work? The 109 known elements are arranged in horizontal rows called periods. The horizontal, if you see the sun and the horizon, is always like that. So that is horizontal. The atomic number goes up as you move across. So you go from left to right and the atomic number goes up 1, 2, 3, 4, 5, 6, 7, 8, 10, and 12. So the periods start with an alkali metal on the left and end with a noble gas on the right. I think I understand why. Just in a moment. The atoms of the elements on the left at the beginning of each period have only one electron in the outer shell. As I said, now it gets complicated with the electrons. They are sorted after the electrons. There are shells, and these shells have an amount of electrons on them. And all the one on the left have just one electron on the outermost shell. Hydrogen has one electron. Every atom has the same number of electrons as protons. It can be more or less when it becomes an ion, so there can be ripped away an electron, and it's just that so will have protons and so on. Or gold can lose one electron. It is also it's possible to remove an electron or give one, but technically it's always the same amount of protons as electrons. Hydrogen has one proton in the center, one electron. It has also, so technically one electron in the outermost shell, therefore it is in the first row. Lithium, it has 3 protons in the center and 3 electrons. On the first shell are 2 electrons, on the first building thing. And then there's a second shell around it, and that is 1. 3, 2 on the first, the third one on the one. So there's technically 1 electron on the outermost shell of lithium. And therefore it is in the same row as helium. Hydrogen, helium, lithium. So hydrogen, lithium. All the one on the left have 1 electron on the last shell. The next one have always 2, 3, 4, 5, 6, 7, and so on. By the end of the period, the outer shell is filled with 8 electrons. Vertical columns, so and the last one have an all 8. Maybe they are 2 a bit together, maybe they have 1, 2, 3, 4, 5, 6. I don't know how it's exactly works. But the idea is, they're having gold has 79 electrons, 2 on the first shell and then always 8. So we're ending up with having 4 or 5 or whatever on the last shell. And every atom with 4 or 5 electrons is listed in the third row. So it's not just listed on 109, but all the 6 one with 1 electron, the next 6, the next 6, the next 6, and then throw them the numbers. So they're not written down like that, but like that in rows, like lines, like writing on the paper. And then also always so set it that they exactly then 1 row is under the number 1, which fits with the amount of electrons to the one up above them. The vertical columns called groups. So vertical, now we're having them. So what did I say? I said it wrong. The atoms of the elements on the left beginning, no, this was right, the left beginning have 1 electron on the outer shell. By the end of the period of shell is filled with 8 electrons. The vertical columns, some of them called groups, each contain elements that have the same number of electrons in the outer shell. Okay, I mixed now something up, I think, but I don't understand what. The elements on the left at the beginning of each period have only 1 electron. By the end of the period, the outer shell is filled with 8. The vertical columns, but these are these ones. They are called groups, and each contain elements that have the same number of electrons in the outer shell. We understood enough. The vertical column is, so they have the same valency and behave in a similar way chemically. It is a bit like that, I don't really understand it, but it could be that my explanation works. It is a bit like if there is one on the outer shell, just one single electron that can be easily lost. It's just one standing there alone. If there are two, a bit harder. If there are 3, 4, 5, and so on. And if it's completely full, it doesn't want to do it. It works similar to that. Maybe it's actually completely right. So it has something to do with these elements are reacting stronger than these ones. I'm not, maybe it's not, I don't know it completely, but basically understand the concept of the periodic table. It works like that. Maybe it's very, but that's the idea of it. Now we don't have time left. Down group. Let's read it and look if you understand one thing more. Down A group. In some groups, such as group 1, the alkali metals, group 2, the alkaline earth metals, and group 18, the noble gases, the group relationship is very obvious. The elements are similar in appearance and reactivity. In other groups, such as group 14, the chemical properties remain similar, but the elements change from a non-metal at the top to metals at the bottom. So they're saying if one knows these elements actually, they are behaving similar. Now let's take one look at the thing we understand. There's palladium that is used in jewelry. There's silver used in jewelry. Platinum is used in jewelry. Gold as well. They're all similar. Gold, silver, they are all heavy, noble, and so on. Found in the same similar amounts. They are rare. Similar. Gold is very rare to find. Silver is rare to find. That's very expensive because they're rare to find. And that's the other thing. Cobalt, nickel. These are all stuffs like metal. They are not reactive, one can touch them without dying, and this is not chemical advice, but basically you can touch them, they can be found in the earth, but rare, they are all worthy, you can make jewelry of them, you can forge them with metal with the same burning, and heat and so on, you can make jewelry, so they're all similar. That was the chemical part. If you don't have to have a wrist stretch training, I thank you very much, and at the next time.